Okay, excellent. So the next contributed talk is Prio Plus, Privacy Preserving Aggregate Statistics via Boolean Shares. This is Eli who is going to give the talk, and joint work with Surya, Kevin, Rafael Ostrowski, and Antigone. Thank you so much.
All right, thank you so much for the introduction. And thank you to all the organizers. Thanks everybody for being here. Really excited to share this work on Prio Plus with you guys. So I'm going to start off by talking about Prio, which a lot of you guys might already know about, but Prio is essentially a system that tries to compute aggregate statistics privately, like a lot of the stuff we've been talking about today. So these kinds of aggregate statistics are really important for lots of different types of organizations, businesses, governments, schools. These are some examples that have actually come into production. So Prio was used to see how it was used for COVID tracking. So the CDC wanted to know how many people in a particular area had contracted COVID, which is obviously very sensitive information. Or it's also in production by Mozilla. Mozilla wants to know, how many people receive cookies from a particular website, but all of this information is very private. And so we only want to compute these aggregate statistics without seeing any individual user data. A lot of the systems that currently exist just compute that in the clear. This is what Google and Mozilla would do for a long time. So Prio aims to compute these aggregate statistics efficiently without seeing any sensitive data. And before Prio, there were some other works that aimed to achieve the same goal. So we've seen some examples of this today. There was randomized response systems, which essentially give you differential privacy guarantees. The issue with the randomized response systems is the privacy guarantees are relatively weak. You still learn something about the client's individual data. You only get an approximation of the aggregate statistic, and there's a trade-off between the privacy guarantees and the accuracy of the approximation. But on the bright side, you do get this kind of robustness property in the sense that if a client misbehaves and they want to disrupt the statistic being computed, they can only affect the statistic by at most ±1. And for comparison, there's also a long line of work using a homomorphic secret sharing approach, and Prio essentially builds upon this type of approach. In this case, you take your data, you split it between a few different servers, and they add up the different secret shares and eventually combine these aggregated shares to get the overall statistic. And this has very strong privacy guarantees. As long as the servers don't collude with each other, nobody learns anything about any individual user's data. And the main issue is that it is not robust. So because the data is secret shared, you can't actually tell whether a client is submitting what they're supposed to submit. So again, Prio's main goal is to compute these aggregate statistics, but with all three of these desirable properties: privacy, robustness, and scalability or efficiency. So just looking ahead a little bit, because I am here to talk about Prio Plus, not just Prio. What we aim to do on top of Prio is essentially to rethink the efficiency model. So a lot of the goals of Prio were based on this scalability metric. So they wanted to achieve very low server communication in order to compute statistics at the scale of millions and billions of pieces of data. And so the one downside of this kind of approach is that you introduce a bit of a burden on the user at the expense of increasing the quality of life for the servers. And so our idea was, well, for these applications where the user device is very low powered, how can we rethink this protocol to reduce that burden on the user? And actually, as it turns out, just improving things for the user, in a lot of cases, ends up improving the server-side cost as well. So we'll see more of that later. So what does the desired functionality for Prio look like? Well, each client is going to hold their own private input. And we want to compute some statistics, some function on the combined inputs of all the users. And the privacy guarantee should be that nobody, servers, clients, anybody should learn anything except for possibly the output of the statistic. And so in this very basic example, each client is just holding a single bit, and we'd like to compute the sum of the bits. So what does the security model look like? We've got n different clients, and some, up to n minus one of them could potentially be corrupted maliciously. And we've got some number of servers, t. And in our case, we use t equals 2. All of our methods can be extended to multiple servers, and Prio's methods are also demonstrated in terms of as many servers as you want, but especially for pictures, 2 servers makes the most sense. And these servers are going to be semi-honestly corrupted, actually. That's a crucial point. Neither Prio nor Prio Plus supports maliciously corrupted servers. You can show that supporting maliciously corrupted servers comes at a pretty dramatic performance decrease. So since you can usually trust servers to, servers are run by Mozilla or they're much easier to maintain. So it's much more common to have malicious clients than malicious servers. But the security properties, again, that we want are privacy and robustness. So clients or servers, whoever's receiving the output, should only learn the output, which is the statistic. And any malicious client should not be able to corrupt the output other than possibly misreporting their private value. So if a client is supposed to be holding a 0 or a 1, they might be able to lie about whether they have a 0 when they actually have a 1, but that should be the worst thing they can do. And the core building block is additive secret sharing. So I'm sure most people here know about additive secret sharing, so I'm going to go a little bit quickly. But the idea is that the person sending the data has some private input, and they just come up with 2 random values that happen to sum up to their private input. And then they can send one of each of these shares to a server, and the servers can reconstruct the private value if they hold all of the shares. But if you only have any strict subset of the shares, it reveals nothing about the private value. And so with just this building block, we can look at a very simple scheme that's been noted a lot in the literature. So this is what most of the very basic homomorphic secret sharing approaches are built off of. And the idea is that the client takes their private bit and they secret share it, send one secret share to each server. The servers aggregate all of their shares that they've received together, and then they publish these aggregates to either the clients, if those are the ones who are trying to learn the statistic, or to the service provider. And the service provider can simply add these aggregates together and recollect the statistic, which is in this case just the sum. And as long as you're working in a large enough group, this returns the sum precisely. And so the obvious problem with this simple scheme is that it's not robust. So we don't get the nice quality that a malicious client should not be able to disrupt the statistic being computed. So if our client chooses 1,000 as their private value instead of a 0 or a 1, they can just secret share this and none of the servers will be any the wiser. And imagine you're using this for a voting scheme. This is really bad, right? Because you can vote 1,000 times for your favorite candidate. So the obvious solution here is to use a zero-knowledge proof. So, again, this is pretty basic, but a zero-knowledge proof is a protocol between a prover and a verifier, where the prover wants to convince the verifier that some statement is true. So in this case, I want to prove that this secret shared value is either a 0 or a 1. And we want to make sure that it's correct. If it actually is a 0 or a 1, the verifier should be convinced. It should be sound, so I shouldn't be able to convince you of something that's not true. And the zero-knowledge property should guarantee that you don't learn anything about my input other than the fact that it's a 0 or a 1. And so if we just apply this as kind of a band-aid to the previous protocol, then we can achieve robustness, right? The client can prove to each of the servers that their input is in fact in the right range. And because of the soundness guarantee, any invalid submission will be caught with overwhelming probability. So by modifying the scheme in this simple way, we get robustness. And so the real interest, people have talked about this solution before. The problem in the past is that zero-knowledge proofs heavily impacted scalability. And so the process of verifying these zero-knowledge proofs on the server side would take a lot of communication, and it would essentially prevent you from doing any kind of applications at scale with these kinds of systems. And so Prio, their main novel contribution is this new kind of zero-knowledge proof called a SNP, a secret shared non-interactive proof. And unfortunately, I don't have time to go into the details. They're very interesting. They're based on a type of probabilistically checkable proof. But the core property is that the server communication to verify a SNP is constant, regardless of the size of the input. So for companies running very high scale applications of these private aggregate statistics, they don't have to communicate much between the servers, which is usually the dominant cost because these servers are housed in different locations and it just costs a lot of money. Now, it would be kind of boring if you could only compute the sum of zeros and ones. So you can actually use the same setup to do more complex statistics by using affine aggregatable encodings, or AFEs. So the idea is if you take your input and you encode it in a particular way, then by summing up these encodings of the inputs, you can actually learn the statistic that you want to compute. So a canonical example is variance. So if you want to compute the variance of a set of data, one way you can do this is you can encode your piece of data x as x comma x squared as a concatenation. And now if you were to sum up all of these encoded values, you would be able to use the sum of the x's and the sum of the x squareds to compute the expectation of x squared, and the expectation of x, and compute the variance by taking the difference. And so a lot of different statistics can be computed in this way. The statistics supported by Prio as well as Prio Plus include variance. You can even do linear regression like this. That's one of the cooler properties, but and or maximum, minimum, lots of different things. And so again, when we analyze the pros and cons of Prio, they are able to achieve extremely low server communication, constant server communication, which is very nice in a lot of different settings. But the issue is that on the client side, when they generate these SNPs, these zero-knowledge proofs, the proof size is linear in the size of your input. So if you're, the larger your input gets, the larger this proof gets. And so the communication between the client and the servers can get a bit high, especially when you're using these more complex encoding. And the client computation to produce the proofs is like n log n, where n is the size of the input. So a lot of extra burden is going on the client to achieve these low server communication costs. Okay, so now to talk a little bit more about Prio Plus. Our core idea is rethinking the efficiency model. So the original efficiency model is, okay, we want to do this at scale with billions of inputs. And so we really need to focus on minimizing server communication. But there's a lot of application scenarios where maybe communication between the servers isn't that expensive, or maybe you're not doing it on billions of inputs, but the devices that you're collecting data from are actually very weak. So especially in the IoT setting, in the mobile device setting, like think heart monitors, think parking meters, you don't have a lot of computational bandwidth to work with. And so in these kinds of settings, how can we still use the benefits of Prio to collect statistics in a privacy-preserving way while minimizing the burden on the client? So that's the main goal that we're trying to achieve with Prio Plus. And the core observation that we use to achieve this is essentially trying to reduce the reliance on zero-knowledge proofs. And so when you actually dig into the details of how these affine aggregatable encodings work and what Prio is actually proving with these zero-knowledge proofs, you find that a very large portion of the work is just proving that your input is the right length. So for sum, for example, the example that we gave at the beginning, all you're trying to prove is that your input is either a 0 or a 1. And you could extend this to a more general case. I want to prove my input is a 8-bit integer or a 16-bit integer. And so if all you're trying to do is prove that your input is some Boolean vector of the right length, there's actually a much simpler method to do this. And the key is to use Boolean secret sharing instead of additive secret sharing, or instead of arithmetic secret sharing, I should say. So Boolean secret sharing is very similar to arithmetic secret sharing, except you're sharing over the domain of binary strings. And instead of normal addition modulo p, you're using bitwise XOR. So in this example on the right, you start off with the string 101101. And if you take a close look at these examples, taking the component-wise XOR gives you the same result. And so the cool observation is that if we do our secret sharing like this, then the work on the server side to verify that an input is the proper length is essentially trivial. If you get two shares, which are each a single bit, then you know that recombining them will give you an input, which is a single bit. So for all of these cases where all you need to do is check the bit length of the input, there's no proof and there's essentially no verification. It's like local XORs. So this is kind of what that would look like. The servers check that an encoding is valid by just checking the length of each share, making sure it's the right number of bits. And then if each of the encodings are the correct length, then they know that the underlying encoded value is the correct length. Or I should say if each of the shares are the correct length. And even if there's other properties to check of the encoding, like for some of these, in the variance example, you need to check that the first part squared equals the second part. Reducing the size of the proof by no longer checking the bit length actually leads to pretty dramatic performance increases. And for some of these cases, we need to perform share conversion because of the fact that the servers need to do aggregation. And so in the cases where aggregation is done via addition modulo p, you need to actually convert back to arithmetic shares in order to aggregate properly. But there's actually a lot of cases, so for and, or, max, and min, the aggregation is done via bitwise XOR. So no share conversion is necessary. You just collect, check the bit length, add them all up, and you're done. So share conversion, I'm going to go through a little bit quickly. But again, we only need share conversion for some of our statistics. And when we do need to do share conversion, we use a form of correlated randomness called DA bits, which are doubly authenticated bits. And these are really useful because they make for an extremely quick online phase. So even though you're spending some time to generate these DA bits at like 2 a.m., on off hours, you get this really snappy online phase once they're generated. So I'll quickly go over some of the statistics that we collected. We have 3 basic classes of protocols, depending on the statistic that we're using. So for statistics like the sum, we have to perform share conversion, but we don't need any SNPs, no zero knowledge proofs. And then the really snappy protocols that we have require no share conversion or SNPs, so that's and, or, max, and min. And the heavier protocols require share conversion and SNPs, which are variance and linear regression. So I'm going to show you guys some statistics for one member of each of these classes. So for some, you'll notice that on a lot of these bar graphs, our bar doesn't actually show up. And so it's usually a good sign. But our encode time is like on the order of thousands of times better than both implementations of Prio. The client message size is also dramatically reduced. The server compute time is also dramatically reduced. So this is one of the nice side effects that we weren't even aiming for. And the expected downside is server communication because we're no longer optimizing for that. But the online communication of our protocol is actually significantly better. And it's really thanks to these DA bits, this offline correlated randomness, that we're able to achieve that. Computing the maximum is even better. I'm just going to go quickly because I'm running out of time, I'm sure. But this is like one of our best protocols, and even the server communication is extremely low and constant. And then linear regression is our more complex one. We require share conversion and SNPs, but for all of our practical experiments, we're still able to beat or close to beat Prio in almost all aspects, except for end-to-end server communication, which obviously includes the time to generate the correlated randomness. And I'm going to skip through this because we're running out of time and go straight to questions.
Thanks so much, Eli, for the great talk. So I would like to ask the next speaker to come, and in the meantime, while we set it up, we can take one quick question if there is any.
Yes. Yeah, so the question is, how do we do share conversion? And yeah, so we're doing share conversion on Boolean shares to turn them into arithmetic shares. And essentially, this DA bit is a single bit that's shared in, it's a random bit shared in both the Boolean and arithmetic setting. And so if you have this piece of correlated randomness to begin with, you can use it to convert the Boolean representation essentially one bit at a time. And the communication is like 1 bit per bit that you're trying to convert. So if you're converting an n-bit integer online, you only have to communicate n bits to convert it, as long as you have this piece of correlated randomness. And actually, we're looking at improvements. So we've recently talked with some other collaborators about a new way to do this, where you might even be able to communicate less than that online. It's a separate multi-party computation protocol beforehand that they run offline to generate the DA bits, but it's pretty snappy. It doesn't take very long at all. Yes. Yes, so great question. The question was, when we have to check extra properties, are we using the same methods as Prio? And yeah, so whenever Prio, the SNPs are really well suited for verifying, especially these like multiplicative properties. So like with variance, checking that x squared equals x squared. So whenever we have to do more than length checking, we're relying on SNPs. So actually, the cool part is you don't. The question was, do you have to verify the consistency between the Boolean shares and the arithmetic shares? As long as you trust the share conversion protocol, then whatever you get out of the share conversion protocol, you just run the SNP on that.
Okay, let's thank the speaker again. So now I want to kind of remind the audience, we're going to have the next talk, and there's going to be a shorter talk at the end. That is the first one that could not take place. So, 1 second.